I'm not this because I don't want to say.
All right,
Okay.
so 3 seconds.
So it's January the 2nd,
Yep,
2018.
correct.
We're in the Alexandra Pub in Wimbledon, and I'm with Piers Corbyn, and this is Bill Smith. And this was going to be just a simple meeting of the minds, but I thought it would be more useful now, having just recently played his video that he created yesterday to celebrate 2018. Thought it would be better.
Actually, we made it on the 22nd of December at a party, and then
Yeah.
put it online
Right.
yesterday.
Yeah. So I'm going to. This is going to be from me. I'll try not to speak too much. I'll try and ask questions, and then this is really a lot of thinking by Piers. And if I do butt in, I'll ask Piers to wink at me and cut me off. All right. So we're structuring this conversation, which should last, let's say, an hour, and in 3 parts. The first part was a short discussion on Mike McCulloch and his quantized inertia theory. And this part of the discussion is completely separate from the climate change subject. I think, Piers, you share my interest in cold fusion and your excitement for it, and the fact that Mike is bringing some new physics thinking, especially in his own style, which means simplicity. And I believe there's a possibility he's bringing an equation into quantized inertia that's as simple as Einstein's E equals mc squared. I don't know that, and that's based on intuition.
Yeah, well, that's essentially the case, yeah. The reason why I'm interested in what he has to say is, first of all, I did a lot of work on galaxy formation myself,
Right.
and I'm fully aware that the standard standard gravitational theories don't work so far as the rotation of galaxies are concerned. So then the idea of dark matter was introduced.
When were you aware of that, by the way? When were
Oh,
you
I was
first
aware of that at least 10 years ago.
Okay, a long time ago.
No, yeah, I was doing this stuff in, it was much before that, 83.
Now, you went to Imperial College London,
Yeah,
which is like the MIT of England.
yeah,
And you studied
physics.
physics.
And theoretical physics. And then I did research there in solid state physics.
Right, okay.
Then I became president of the student union.
Right.
And then carried on doing research there, but there were political difficulties, which meant that I didn't complete, and later on I went to Queen Mary College to do an astrophysics. So I graduated in 65,
Right.
was president of the student union 69 to, I went to Imperial in 65, graduated in 68, went to, was president of the student union 69 to 70, went off for a while doing squatting and radical activity 72 onwards to about 80,
Right.
and 1981, in 82, I did an MSc part-time in astrophysics at Queen Mary College, and came back to Imperial as part of those studies, where I went to Professor Kibble's theoretical physics lectures and so forth.
So I went to King's around the 65 to 68.
Okay,
Did
so you're the same age as me then?
Yeah, and I know I look a lot older. And and I know studying physics inside the special mathematics. It was almost, although I studied under Bondi, special relativity.
Oh, right.
And I've got some amazing Einsteinian stories, and felt I was being taught by Einstein. It was almost like they didn't really want us to understand it.
No, that's what I think about the relativity aspects of stuff as
Do
well.
you? Yeah, it's very strange, isn't it? And therefore, the simplicity, if I could just add something to this conversation, one of the stories Bondi used to give us is that the way Einstein discovered or first started to think about special relativity was in a train in northern Italy, in a train station, where in the carriage next to him there were two lines. There was a beautiful woman, and the beautiful woman started to pull away from the station, and it was at that moment that his mind went into confusion, because he wasn't sure if he was leaving the station or if she was. Okay. And I had that same experience, and therefore I look for simplicity in every complex hypothesis, and that's why I'm excited about Mike, because Mike instantly said, I'm going to think about cold fusion on the train to Edinburgh. Okay. And I think I've had not a solution, but a contribution that's going to be profound. So tell me what you think. Are you able to explain quantized inertia? Would you rather not try? Because I've been trying to get him to explain. I asked him to explain it in a 10-slide PowerPoint, and he came back with a single image. And he said, Bill, I don't like 3 image explanations, I like 1. And because he's a brilliant cartoonist and artist, right, he feels he's explained it in a single image. And I'm not quite there yet with it. What do you think about what he's...
Well, I think it's brilliant. But I first of all put a bit in about why... The background is why I think it's brilliant. So I'm doing this galaxy formation stuff, and did an MiHsC in it, and the MiHsC involved writing a paper that was in the Italian Physical Society journal, presented at a conference I went to in northern Italy, and that was about I devised some equations for application in an expanding universe, which involved dark matter or not dark matter. And the point is that then I started to conclude that the idea of dark matter was nonsense, but therefore the theory of galaxies as they are is inadequate.
Again, what year was that?
That would have been 83.
83, okay.
Yeah. Or maybe, yeah, it was 83. After that, though, I went on doing teaching and then developing ideas of long-range forecasting. So I left my galaxy stuff aside, although I did give some talks about various theories of galaxy formation, some of which involved what's called the cosmic string loop theory of galaxy formation, which is, I wrote a paper on that. But these are string loops as big as the early universe.
So is this the Mach you mentioned?
Yeah, the Mach's principle we'll come to in a minute, okay. Right? But so I had this view then that there's something fundamentally wrong, and I noticed in astrophysics that they do tend to get obsessed with ideas, and different camps of people then go on shouting at each other without doing too much listening. For example, there was a time when one group said that the Hubble constant was 50, and there was no way it could be above 70. And another group that said it was 100, and there's no way it could be below 70. So these people would never have a discussion. And then one professor came along and said, well, he thought it was about 70, and they all screamed at him and said he was wrong.
And that, just out of interest, where is it? What is
the Hubble constant? Yeah. It's a sort of measure of the rate of expansion of the universe.
Oh, okay. Yeah, but what is the number though?
I think the official number now is nearer 50.
Okay.
But it's now deemed maybe it's a variable.
Okay.
You see, so you could argue whatever,
yeah.
you know.
So if I can just ask a quick question. When we look at the Hubble, I think it's not the Hubble image, it's the image that we're currently looking at to see the scope of the whole universe.
Oh, right. This thing, the so-called photo of this Big Bang.
Yes, yeah. And it's almost a mesh.
Yeah.
And it's not a disciplined mesh, it's a chaotic mesh. But are the strings that you see there, are they connected with what you're talking about?
No, probably
okay.
not. Probably not.
All right, I'm taking up on a tangent. Let's go back.
Okay.
Let's go back to,
so Mike, I'm interested in what Mike had to say.
Right. Now Mike's a prof at Plymouth, University of Plymouth, right?
Yeah. Okay.
Okay, in physics.
Okay, well, the first thing that I thought was good is that he has ideas which can explain rotation of galaxies. And second thing is, I came along when I met him with a few equations using combination of the 1 over r squared and 1 over r force, if there is a 1 over r force, and that can very easily show that the rotation rate, the rotation of the stars outside the centre when you go to the edges, it's going to be constant. The speed is constant, that is, and the size of all spiral galaxies will be about the same, and that is pretty well true. See, so I asked him, well, okay, can your theory give a 1 over r force effectively? He said yes, it does. It is effectively a 1 over r force. Okay, now what's it about? Well, oh, sorry, before I do that, about Mach's principle, I said, well, I like it then because it's consistent with Mach's principle. Mach is M-A-C-H, as in Mach 1, Mach 2 for the speed of sound and so on.
Which we say in North America, Mach.
Mach, yeah.
Yeah.
But not Apple Mac.
Mach 2, yeah. Okay.
Right, so Mach's principle then is that the distant matter of the universe fixes the frame of non-rotation here. Now that is obvious because you look in the sky and if something is rotating it's relative to the distant stars. So how can this be?
It's relative to the centre of gravity of the dominant controlling object.
Well, maybe, yeah. But you see, if you've got on a 1 over r force, then as you go out in the universe, roughly speaking, the amount of matter goes as r squared. So r squared over r is proportional to r. So the material further away is having the biggest impact.
All right, now stop, because for anyone
essentially,
listening, we can look at the solar system with the sun at the centre and the planets and their moons. We can look at the galaxy with a black hole in the middle, and we're 2/3
all of that
way
will be
out.
run by r 1 over r squared.
And it was, but I didn't realise that. I thought that what QI was relating to was just a given galaxy inside. I didn't think you were also that Mike was also talking about dark matter, intergalactic dark matter.
Well, the people that want to save their theories of the standard theories of gravitation and general relativity only need dark matter to be in the cores of galaxies. But they don't want it anywhere else.
Okay, so it's inside the galaxy.
Yeah.
Okay, all right. Okay.
Right. So his idea is that you have some sort of waves. He calls them information waves that cover the whole universe, right? And if the wavelengths, there's only certain wavelengths as big as the universe can exist, and the effect of these things is that they make a force.
Piers, I've got to stop you, because I think anyone listening to this is going to understand, I might not even know, Mercury goes around the sun a lot faster than the Earth goes around the sun. And the Earth goes around the sun a lot faster than Pluto. So the closer you get to the centre, or the closer you get to the outside, the longer, the slower the speed. So it's not like a plate.
No,
it's almost like rotated.
Absolutely.
Right. Whereas on the galaxy, when you look at the edges of the galaxy, the solar systems on the edge of the galaxy are as if they're stuck on a plate, the same as the solar systems in the centre.
That's right.
So it's like a plate going around the black
exactly.
hole. That's the problem.
That's right. It's like very good. That's a very good example.
All right.
It's like a spinning plate, which is completely unexplained in terms of the 1 over r squared force.
Okay.
But if you have a 1 over r force, you can explain it totally.
Now I'm getting your point better. That's why you were making the point.
That's right.
Okay. So can you spend a bit more time on that?
Well,
because I think it's fundamental.
Right. So these are the notes I made. Funnily enough, on a train on the way to meet Mike, which was as follows. There you are. So people can listen to this. When you have the 1 over r squared force, big G times the mass within a certain radius divided by r squared times m1, which is the test mass, equals m1 v squared over r.
These are Newton's laws
Yeah.
of planets rotating around the sun,
Yeah.
basically.
Yeah.
Okay.
Yeah. Now, if you use, say, a spherical object, the mass within radius r is 4/3 pi r cubed rho, and then you put that equal to v squared over r, then you get, or mv squared over r, then you get v goes upwards linearly with distance. That's what happens near the cores of galaxies. That is observed.
Okay.
So that fits. But when you get further out, you have a completely flat thing like it's rotating at a plate. And if you then write another equation, some constant times the mass, which is now just going to be the core mass, times m1 over r equals m v squared over r. That's the acceleration. So the r's cancel and the v is constant, and that is observed.
Okay.
So, and that, you see, as you go further out, the 1 over r force is going to dominate, because the 1 over r squared force is going to get smaller and smaller as you go further.
Yeah, but okay.
Relatively smaller.
All right. You're feeling strongly that you understand it from what really is high school mathematics,
Yeah,
isn't it?
that's right. This
So
is a
where's
simplified
QI,
way.
though?
Oh, well, where's QI? See,
Okay.
QI can explain where the 1 over r force comes from.
Comes from. Okay.
So really what QI is saying is somehow the distant universe defines how these interactions can take place. Now, I can't say I understand it well, but the idea is that you have these, he calls them information waves. I don't like the idea of information waves, but waves in some whole cosmos.
Well, can I stop you there?
Yeah.
Okay. Because this is where I.
A bit like quantum mechanics, you see, but on the
it's
scale
definitely.
of the universe.
Well, I said to him, I told you about this diagram he drew, this beautiful single diagram, which basically, if you know about the M drive, the conical drive that NASA's discovering. If you let microwaves loose inside it, it generates a propulsion forward, right? Well, that's part of this situation. And what I said to him was, his diagram almost looks like the conical M drive. And he basically, it's not quite the shape, but what he says is, because of the speed of light, and he calls it the informational horizon?
Well, there's various things, but he may well do. They're called Unruh or Rindler waves.
Yeah, and that's something that anyone listening to this needs to learn about and research. And Mike has written a fantastic paper where he's made a real effort and a beautiful video, so the listener can get information on that. But here's what I said to him. I said, does this concept apply to the universe, to the galaxy, to the solar system, or to atoms? What level? You call it quantized inertia. What level are you talking about, Mike? It's not clear. And you know what his answer was? What do you think?
Well, it should have been everywhere.
That's exactly. It's exactly what he said.
Good.
It's every point, and everything is pretty much. It's like fractal mathematics. No matter what your scale is, it's equally applicable. Okay, sorry, I'm cutting.
So that's essentially what it. So far as one can explain it, what it's about.
And why do you think why you support? You're relatively supportive. What is your position on it?
Well, I agree with it.
Oh, you actually say you think he's got something?
Yeah, absolutely. So as far as I understand, we talked about the Casimir effect and how there's different ways of explaining that, and he came up with some Unruh-Rindler wave answers to that. But I did raise some problems about acceleration relative to what? Because you see, if there's an acceleration, then there's something making the acceleration. Things don't just accelerate. So the stuff has to be then about some local force and how that and its relationship with that and the distant universe, which is interesting.
Well, you see,
Okay.
Sorry, I don't mean to.
And if something's accelerating under gravity,
Right.
it's under free fall. So there's not a local force experienced by something accelerating under gravity, but it is, of course, accelerating relative to the distant universe. So, well, there's many questions needed to clarify what he means, but the point is his ideas of these waves does appear to work, and it's consistent with Mach's principle that the distant universe governs things, and I'm wondering if it's going to be consistent with what I call the full Mach's principle, which is my phrase, which is that the speed of light here is actually determined by the speed of recession of the distant universe, as opposed to it being an absolute constant of space and therefore limiting the speed at which the distant universe moves away, which I think is a back to front way of thinking about it.
Well, I hope that sounds really interesting.
But see, all this means is that if you have an expanding universe, then the speed of light is changing.
Yeah. And there are lots of people who...
And there is evidence
that.
now that apparently the speed of light does change. Like the fine structure constant, when it looked at stars above the galaxy, above the plane of the galaxy, which is similar to the plane of the Earth's orbit, is different from when we look below the galaxy. So the fine structure constant seems to vary, which is E squared over 4 pi epsilon naught h cross c. So the c might be changing, or the E squared might be, whatever, but something's changing.
Right. So I wanted to, before we move on to, I wanted to think about cold fusion and Mike's intuition that, because he did think about it for not more than a few days and came back and said, much to his surprise, because he hadn't studied LENR, much to his surprise, when he got his hands on a few papers, he started to understand the cracks in, I think it was the palladium. He suddenly started to see visually, which I don't see, but he sees visually a condition that is similar to the other conditions he's seen before. And I think he's produced a paper on it. He's not had it published yet. I've not seen it, but
he said he was producing a paper on it.
Did he? Okay.
Yeah. Well, yes. No, I don't know what he's saying, but you see, these cracks are a bit like perhaps the Casimir effect, with plates of material very close together and forces turning up, some of which you can explain in terms of his model.
Right.
So now, the idea of cold fusion is, well, it's great insofar as if you can understand, if you can get two nuclei very close together, then they could interact. So that's all the theory's about. And how can you trick them into being very close together? And he's saying, well, maybe in the palladium this can happen, and he's describing how. Now, of course, for the mainstream people, this stuff is dangerous because it affects the belief in general relativity. I mean, it may or may not, but they probably see it as a threat. You see, I think general relativity with its ideas of curved space-time and so on is pretty inadequate, and I think it's overrated. And it may be this idea could substitute or replace general relativity. I don't know. But maybe it can.
Well, perhaps I can share with you a small insight I had on the actual mathematics, the equations, and having studied, like we all did, Newtonian mechanics in high school. When I finally got to special relativity, and I studied Lorentz transforms and so on. There was no continuity between what Newton had created against what Einstein had created. And it was only many years later, I won't tell you the book it was in, but it was basically by a guy called Schroeder. And it was about have you heard of the Aurora TR3B? It's the advanced plane that's meant to work on anti-gravity. It's a well-documented classified American plane.
Oh,
It's often seen as a triangle with 3 lights.
Yeah.
You know, it was over Belgium for several years ago. It's what everyone calls a UFO.
Yeah, well, I've heard stories about it, but
yeah.
you're saying it's an American experimental
It's
thing.
more than experimental now. They've had generations of models. But the book that was written about that explained the propulsion, in the appendix, gave a beautiful summary of mathematics. And it for me, as an ex-mathematician, it took me back through my high school mathematics in 5 pages. Then it led me into my undergraduate mathematics, and then it led me into what was basically a description of quantum mechanics in mathematics, simple mathematics. And what became really clear was that you could show Einstein's equation, E equals mc squared, as an extra term on Newton's equations.
Okay.
And when I say term, if you take for the non-mathematicians, it's basically any let's say actually all I'll say is everything is an approximation, and that Newton had a pretty good approximation to the way objects worked on Earth. He didn't take into account the fact the Earth was spinning, or it was going around the sun, or the sun was going around the galaxy. All it did was pretend the Earth was flat, and that's all it did. So what Einstein's equation is an extra term on top of that that zeroes in the hypothesis. So you can look on it as just an improvement to the hypothesis. Well,
if you want,
all right, and so most people, and even Einstein, wanted it to be a completely new way of looking at things. But in fact, it was just zeroing in on the hypothesis. So I think what might be doing is adding a third term. If we say Newton had term 1, you know, you say 1 over r squared, 1 over r cubed, 1 over r to the 4th. What I believe might be doing is adding a third term to what Newton, Einstein, and now Mike is actually how he's defined it. But it in itself can be reduced to something very, very simple, which includes Planck's constant, and that's where I get, Planck's constant. It was not in my training. So we've talked about Mike. You've given great support to. I think at best we can encourage other physicists to take very seriously what he's done, and really take a time to understand it. And
I think the important things, I summarised the important things here. I asked him why it's called quantized inertia, and he explained it's in terms of these information waves.
Right.
I asked him, could it provide an effective 1 over r force, and he said yes, which to me is a clinch. It really clinches the argument. Right. And I pointed out that if it's true, it can effectively give some sort of anti-gravity force, which is something you just mentioned. I talked to him about this idea of the speed of light, whether it depends on the distant universe or not, and that's something we left to think about. I talked about grand unified theories of physics, and my suggestions on these is that somehow that maybe gravity is some sort of a different way of looking at electromagnetic forces. However, all that is a bit esoteric, but the most important thing I would say is that his theory is consistent with Mach's principle, and I think any grand unified theory of physics has to be consistent with Mach's principles, and all the ones hitherto are not consistent with Mach's principle.
Okay, so I think that we're both in agreement that he's definitely a great, good
he's onto
young
something.
physicist.
Absolutely.
All right, so I'm going to pause right now and.